Mars. The Martian planet has secrets. The way to those secrets, of course, is to go to Mars. But before that, Mars can come to us. I welcome Professor Meenakshi Wadhwa. The professor is a foundation professor at Arizona State University, most importantly, the director of the School of Earth and Space Exploration at the university. Also, another hat, Meenakshi is the principal scientist for the Mars Sample Return Program, pending. Professor, a very good evening to you. I begin by saying that the Mars Sample Return Program is in the news much because of the debates having to do with money, but that's what Washington's for. The mission is to finish out the first part, which is being performed right now by Perseverance. Perseverance is the second most important rover on the planet. The other one is Curiosity. I'm partial to Curiosity ever since Opportunity went
right.
very quiet. However, the samples are there. It's time to go and get them. Professor, congratulations, because what brought my attention immediately was your excellent essay in the Nature magazine, the peer-reviewed top-of-the-pile magazine in Europe, matching science in the US, making the very strong case what bringing space rocks back to Earth will achieve. Thank you very much. Let us begin at the beginning, the Apollo program. What did the return of moon dust teach us about our solar system, our planet, and the moon we gaze upon? Good evening to you, Professor.
Good evening. It's a great pleasure to be here, John. So starting at the beginning, like you said, at the Apollo samples, I mean, those samples really completely revolutionized our understanding of how the Earth-Moon system formed, how the moon originated, and it also told us something about the dynamics of our solar system. So there was a lot that we learned, and there's not enough time to tell you about all of the details, but just some of the highlights, right? There's, before we went to the moon, before the Apollo programs, the thought had been that the moon, we really had no understanding of how the moon came about, whether it was a captured object, whether it was accreted at the same time as the Earth, whether it sort of was, basically a part of the Earth, and there was a fission process that formed. We had no idea at all. However, once we got those samples back from the moon, we started to get a really good understanding by looking at the chemistry of these rocks, by looking at the mineral compositions. We started to see that the moon could not have been cold. There was possibly a magma ocean on the moon at some point in the past. And the whole idea of magma oceans on planets, that actually came about from studying moon samples. And we basically also learned that the moon may have formed by a giant impact, possibly of a Mars-sized object, basically colliding with the Earth sometime like 4.5 billion years ago, and tossing out this huge debris cloud of gas and dust that then accreted to form the moon. And so, all of this, and also understanding kind of the flux of material falling onto the Earth and moon, that understanding came from studying moon rocks. And so we really learned a whole lot about how terrestrial planets formed, and how these moons might have formed, how magma oceans on planets evolved, and the dynamics of the early solar system. So there was a lot to learn there.
Yes, and the moon dust is a way of talking about the future, because we will study the solar system robotically and in terms of samples before we will put boots on the ground. So let's go to the successes, because we're building a case for the Mars Sample Return mission, why it's necessary. Right. In the news, every time sample returns from the asteroids, you have a list in your excellent article, Itokawa and Ryugu, and what we learned from those small pieces of asteroids. What are we looking at when we look at an asteroid, Professor?
So the asteroids in our solar system are basically remnants from the earliest history of our solar system. So they're all close to around 4.5 billion years old. That's when we think that our solar system came together from a cloud of gas and dust in this sort of neighborhood of our in our galaxy. And so we are learning something about our very origins, about the origin of our solar system, what the bulk chemical composition was that we originated from, what were the kinds of inputs from other stars that actually created the material that actually formed our solar system and planets. All of that we can understand from studying asteroids. And one of the key things actually that we're learning, particularly from some of the samples that we've just very recently obtained, and in fact, you've probably heard of the Osiris Rex mission.
Yes.
That just came back, and they're starting to look at that. And that material came from an asteroid Bennu, and that's a carbonaceous asteroid. And there was another mission by the Japanese space agency called Hayabusa 2, which brought back samples from another carbonaceous asteroid called Ryugu. And looking at these very primitive carbon-rich asteroids, most of which actually they're thought to contain organic compounds as well, we're starting to learn a lot about what were the initial ingredients that formed the terrestrial planets. Could these materials, could these carbonaceous asteroids in particular, have brought us the building blocks of life on our Earth? And so we are really kind of, these objects are giving us a window to look back into the deep past of our solar system and the formation of our own planet.
I think of it as a detective story, Professor, following this news over the years. You have theories, and then you have evidence, and they don't match most of the time. So you have to come up with new theories, and then you get, let's go get some more samples to make sure we're right. So it's wonderful. You're building on your successes. There's another mission, the Stardust mission.
Yes.
Comet Wild 2. Comets and asteroids, they're different bodies that sometimes come into our purview of the solar system. Comets come from, I believe, help me, the Kuiper Belt, which is beyond, it's trans-Neptunian, beyond Neptune.
Yes, so a lot of the comets are thought to come from very, very much further away in the outer reaches of our solar system compared to asteroids, most of which at the current time are basically between the orbits of Mars and Jupiter. And we think most of these asteroids formed in the inner parts of our solar system, and the comets formed in the far reaches of our solar system. So they sample very different objects by and large. And so the comet Wild 2 was, the tail of that comet was sampled by the Stardust mission, and it collected these tiny little particles. I mean, the total amount of material that we brought back from that comet was probably about 1 milligram or so. And so even with that small amount of material, we learned an incredible amount, again, about the dynamics of our solar system. We actually found, and we had expected actually to see mostly unmelted pre-solar particles in that cometary material. What we found instead was actually minerals that were formed as a result of very high temperature processes. And that must have formed in the inner parts of the solar system, but that were transported out somehow to the very far reaches of the solar system where the comets formed. And so it's telling us about something about the dynamics in our solar system that we did not know about before.
Yes, you just remind me. I didn't put it together before. We're speculating now about the movement of the planets as the solar system formed.
Yes.
The inner rocky planets and the great big Jupiter and Saturn, there's some resonance between them that might have made it possible to migrate. Do I say that correctly, Professor?
Yes, I mean, so there's now a lot of hypotheses about what might have happened in our own solar system in terms of the planets where they currently are at the present time, the current architecture of our solar system. It most likely was not, it did not start out this way. And so we understand possibly there might have been migration of the giant planets from the inner parts of the solar system closer into the sun towards the outer parts where they are currently. And that might have actually scattered a lot of the small bodies and objects, asteroidal bodies, and may have actually caused the flux of material. We see actually a flux, we think that there was maybe a huge influx of asteroidal materials falling on the Earth-Moon system early in the history of our solar system. And that's declined at the current time. And so I think it could relate to that migration, early migration.
Is that what's called the Great Bombardment or the Lesser Bombardment? Something like that.
It's called the heavy bombardment, the period of
Heavy
bombardment. And that's also, I mean, it's a debated thing, whether there was a peak or whether there was just a high flux that declined over time. But there are things like that we are, trying to understand because of these types of samples that we've now got in hand and can analyze in our laboratories.
We're headed to Mars, but there's a fun story that's just come up. Osiris Rex, the professor mentions, a sample return mission. Osiris Rex is a robotic probe. It's on the way to more adventures, but meanwhile, it is returned from Bennu, an asteroid, a sample that, according to the news, is our cup runneth over. What have you learned about this sample, Professor?
Well, the team is actually in the process of disassembling the canister and the sampling container that was brought back by the capsule from Osiris Rex. And so they are actually finding that there's more material there than they had even anticipated. And, originally, I think the thought was there might be something like 250 grams or so of asteroidal material. And they're finding a lot of dust and particles on the outside of the actual, what's called a tag SAM, which is the touch and go sample acquisition mechanism that has basically contained within it the sample. And they're finding, just as they open the canister inside the lid and around the outside of the canister, they're finding a lot of particles and material. So they're very methodically collecting that so that they can also include that as part of the analysis, and then they will open up and discover how much material they actually have inside of the tag SAM.
Is Bennu a carbonaceous chondrite similar to Ryugu?
So carbonaceous chondrites are the meteorites that we think might be the closest analog of the kinds of materials that we have brought back from Bennu and from Ryugu, actually. The Ryugu samples that we were brought back in 2020, those are actually most similar to a type of carbonaceous chondrites called the C1 chondrites. And they're thought to be some of the most primitive materials in the solar system. They've not undergone hardly any kind of processing except for some kind of, water interaction with water on the surface of that asteroid. And so we think that Bennu might be similar to that kind of asteroid, or it could be another type of carbonaceous meteorite. We have to analyze that material to understand exactly, what it is most similar to, if we've seen that kind of material before in meteorites or not.
So what I'm putting together anecdotally then is not just a detective story, but you're learning how the solar system was put together. That would be highly useful given all the work they're doing on exoplanets now to see how similar or different we are from other solar systems.
Exactly. So, I mean, we're going to learn in so much detail the chemistry, the chemical and isotope composition of the material that's going to be brought back from Bennu. And the important thing, we've got these meteorites, but the reason why we want to bring these asteroidal samples back is because meteorites have been sitting around on our planet for many of them for decades or centuries, and they've interacted with the Earth's atmosphere, with the water and organics here, and so they're not pristine. And so these materials that we brought back, they will really be able to tell us what is the pristine organic and water and volatiles that were in these asteroidal materials, and did they contribute to the prebiotic chemistry that basically led to potentially the origin of life on Earth.
All these clues. Sherlock Holmes once more. So we're headed to Mars now.
Yes.
Professor Meenakshi Wadhwa, she is the director of the School of Earth and Space Exploration, a foundation professor at Arizona State University, but importantly, the principal scientist on the Mars Sample Return Program. Professor, the budgeting is something we can't solve. However, we know it will be solved. Why do you want Mars? We've talked about the probes of our solar system. We've talked about asteroids and comets. We've talked about the moon. What will Mars teach us?
Mars has a lot to teach us. I mean, it's our sister planet in the habitable zone in our solar system. It's the other terrestrial planet that we think early on in its history, it likely was very Earth-like. And we know that from we have, a couple of decades of exploration of Mars. NASA has invested and orbiters and landers and other rovers, like, and you mentioned the Curiosity rover, of course. And so there's been decades of work that's been put into Mars exploration to understanding the geologic context. And basically what we've learned is that early in its history, Mars was a much different place. It was much similar to what we think Earth might have been like, with potentially standing water bodies, oceans on the surface, maybe a thicker atmosphere, maybe a warmer climate. And so on Earth, we don't have any rocks actually that date back to, much older than 4 billion years. There's maybe less than 1% of Earth's, surface that's that older than about 3.5 billion years. On the planet Mars, however, greater than 50% of that surface is older than 3.5 billion. And that's that time period when it was very, we think, Earth-like. And so, we can really understand something about the conditions, the environmental conditions that might have given rise to the origin of life on our planet by looking at environments similar to that on the planet Mars. And so I think it's not just understanding, just finding it's about finding life, of course, if there was ancient life on that planet, but it's about understanding the geologic context where that life arose, how that life arose. And so I think that this is our nearest term opportunity to answer the big question: are we alone in the universe? I mean, I think this is the closest opportunity that we have to do that, and to understand the geologic context along with it. What did it take to basically have life originate under those kinds of circumstances?
Mars is a time machine. That it's going to take us to a moment in our formation where we were part of the solar system and Mars was part of the solar system.
Exactly.
And what happened here, we can't explain yet, as I recall.
And by the way, I mean, one thing I will say is that whether or not we find life in these rocks, I mean, it's going to be a huge, moment of sort of understanding of how and why and the conditions under which life can arise. Whether we find it or not on Mars, it will tell us a lot about, if the same kinds of conditions, if we think the same kinds of conditions are on Mars, if life did or did not arise, what can that tell us about how common life is and what were the conditions and how did it arise? So I think, it's going to reveal a whole lot. Either way, whatever that we find about it, I think it's going to be revelatory.
We just have a moment here, a minute left. You've been very generous. As principal scientists, you're waiting for decisions made in budgets. I understand all of that. But those samples, they will remain until you get there. Is that correct, Meenakshi? They're not moving. They're not at any risk. Those are part of the future.
Those are part of the future, absolutely. But we would love to be able to bring them back as soon as possible, because otherwise, they'll obviously be sitting, waiting for us to go get them. But they have stories to tell us, and we want to know what they can tell us, those stories.
Professor Meenakshi Wadhwa, Director of the School of Earth and Space Exploration, Foundation Professor, Arizona State University, Principal Scientist for the Mars Sample Return Mission Program. This is CBS Eye on the World. I'm John Batchelor.